but I thought all the other schools had them too, and it was just like a stupid practice that we all do anyway.
No.
What, 506?
Oh boy. Okay. Okay, so here we go. We're going to talk about a very special kind of series today. All right, and the series we're going to talk about today are called power series, and they look a very particular sort of way. And a power series actually captures a whole class of series. Okay, and the reason we're very interested in power series is because of the series, of the kind of series that do a good job at modeling other types of functions. Power series are one of the good series at modeling functions. Okay. So power series, and then we're going to talk about Taylor series and Maclaurin series, which are types of power series. Let's see. All right, so this is what a power series looks like. Okay, it's in this form. And notice that a power series is a function, right, of x. So power series looks something like when you plug 0 in, you get C0 out, where C0 represents the 0th coefficient, right? The coefficient of the 0th term. Then when you plug 1 in, you get C1 x to the 1. C sub 1 means the coefficient of the first degree term, right? And you actually know a very famous power series. You want me to introduce you to him or her? Are you all right with this? Can I introduce you? Okay, so here's your introduction. You know that power series. Talk to me a little about this power series.
Infinitely increasing?
Yeah.
Diverge.
I don't know. See, I don't know like that it's definitely infinitely increasing. I don't know that it's definitely diverging. Doesn't that depend upon what x is? Tell me this. What series is this? Like, what am I doing to get each term?
The geometric series.
Say it loud and proud.
Geometric series.
Geometric series. What's my r?
X.
R is x. So first of all, this is a power series. Second of all, it's a very special kind of power series. This happens to be geometric. Now I really want you to focus on this though. What's the big difference? The big change is, hey, it's now a function of x. I'm not telling you like that the ratio is 1/2 or the ratio is 3/4. I'm telling you the function is x. Now, does it converge or does it diverge?
Well, it depends on what x is.
It depends.
If x is if the absolute value of x is greater than 1, then it's going to diverge.
You know what? Go the other way because I'm really concerned about when it converges.
So if the absolute value of x is less than 1, then it's going to diverge.
Great. Perfect. That's great. All right, let's pause there. Soak it in for a second. Is that okay?
Is that like one of the conditional convergence things?
So this converges absolutely when the absolute value of x is less than 1. There are some issues with what happens when x equals 1, but I'm going to hold off on that right now. And so this, I guess, this is a little different than when we defined conditional and absolute convergence. This is just saying, hey, this converges when this is true. So, is that okay? What's like the question that you're dying to know? Maybe you're not dying to know.
What does it converge on?
Yes, exactly.
Can you do 1 minus, like, can you do a over?
Hold on, just wait one sec, all right? So, the big question is this. Sorry, I'm getting a little enthusiastic. I gotta calm down. the big question is this: great, I have a series here. What does it converge to? That's been the whole thing that we've been working up to, right? Tell me what function this looks like, because that's why I care. I care because I can tell you a series that looks like a function, and it might be easier to compute than that actual function. So, what does it converge to? We will be able to answer that question a little bit today, but we're not going to recognize a lot of the series that we're going to deal with, right? So part of what we need to do over the next couple of weeks is say, hey, what are the series that I really care about? We got a bird's nest back there. What are the functions that I really care about, and what are the series that correspond to those functions that I really care about? So, hey, we know that this is a infinite geometric series with r equal to x, and the a is equal to 1. So what's this equal to?
1 over 1 minus x. And you can just say that it mirrors that function.
Let's take a look.
It's pretty cool.
So let's take a look. So I need to pause there. First, are people okay with the fact that this is an infinite geometric series, and that, I don't know what I just did. I did something that was not good. There we go. And that's what you learned in Algebra 2, right? So a in this case is 1, and r is x. Is that okay? All right, let's see. Turn this guy off. Whoops. All right, so you can do it in y1 and y2. I'm going to do it in y3 and y4. You can just watch if you want. I don't really care. So the question is this. 1 over 1 minus x and 1 plus x plus x plus x to the third. I think I'm going to stop there for now. Okay. And I'm going to try to make y4 bold. All right, so let's take a look at the graph. There's y equals x, and there's that. This is a terrible window, huh? I'm going to try to do maybe zoom decimal, see if that helps. Huh.
It's pretty good there.
So it is pretty good. Where is it pretty good?
At the beginning. After it passes 0.
So maybe a little before 0, right?
Like a deployment function.
And up till...
Up to where...
Should I get a better window? Let me get a better window. Okay. I'll do like -2 to 4, and then I don't really care about, I'll do like 0 up to, I don't know, 10.
Really only okay up to like 1.
All right. And then
If you add more terms.
okay, so let's
Yeah.
try. Let's add, I mean, I'm not going to go too crazy here, because the point actually is that we're trying to come up with a simple function that models
Right.
the geometric series. And if I have to go out to 8 or 10 or 12 terms, that all of a sudden is not as simple, right? X to the 4th plus x to the 5th. Better, right?
Yeah.
And I don't know if you saw, if I add an even number of terms, I will go and I'll add plus x to the 6th. Whoops.
It'll curve around the other way.
Yeah, it's going to be... So right now... Oh, boy. I'm trying.
Oh yeah.
Right now, I know we're starting with a 1, but the leading term would be x to the 5th, right? So that's an odd function. And if I did... Come on. Plus... Nope, still wants me to... Still thinks I'm arrowing over. Plus... Now I made it freeze. No. X to the 6th.
Oh, you multiplied that one.
I am really not doing well this morning.
Oh, so it's just
Right right? So it does this. So do you want to talk to me about where it looks like it fits well?
Up to
Up to 1 and from
Negative
-1. And doesn't that make perfect sense? Because when does it converge? When x is between -1 and 1, right?
Oh yeah.
So this is your first friend, your first power function that we're introducing you to, and this is a geometric power series, all right? And it does a great job at approximating the sum of a geometric series function as long as we're on this small interval. Now, hey, if you wanted to get wanted to do this another way, not that you'd want to, but you could. What if I actually did 1 minus x? How many times does that go into 1? All right. 1 goes into 1 how many times? 1. I multiply. All right. 0 minus negative x. All right. How many times does 1 go into x? X minus x squared. All right. 0 minus negative x squared. How many times does 1 go into x squared? You see what I'm getting?
Yes.
So when I actually divide this, I'm getting 1 plus x squared plus x cubed plus x to the 4th,
But you
right?
couldn't start with
Kind
that.
of crazy.
Say again?
Like you
Well, yeah, I didn't. You'd have to get really lucky to guess that this was the function, right? But it's nice to know that your Algebra 2 teacher told you something that was true, and that's absolutely right if you work from the other way backward, right? All right, that was a lot. That was a lot in 10 minutes. I'm going to pause. I have so much more, but I'm just going to stop for a little bit, for like 8 seconds. I know. Doesn't sound like a lot when you say it like that. But it is awkward. It's a long amount of time if I'm actually quiet for that amount of time.
You hear the sounds of our young.
I get something annoying, right?
All right, that was 8 seconds. All right.
What is the
I
next
had much
question
more
last
coffee
week?
today.
Okay. Yeah, all right, great.
You're such. Life sucks to you, Dan.
Oh, look, we know that. All right, so, hey, here's a power function that looks like a geometric series, a power series that is a geometric series. So geometric series is a type of power series, and we learned to know and love that. Okay. A general power series looks like this. Okay, so we took a very specific example, and we say that if you think about our graph, this is a power series that's centered at 0, meaning that it's a good approximation at 0, and hopefully some amount to the left and some amount to the right. Now, it doesn't always have to be that way, okay, but it's a good approximation at 0 at the very least. Now, what would be better? It'd be better if it went even further to the left and right, right? If the approximation was good for all values, but this one isn't. This is a power series centered at A, right? So it's like, do you remember in Algebra 2 when you did horizontal shifts? Say yes.
Yes.
Yeah, great. That's sort of what we're doing here. And here, like the synonyms, we call it a power series in x minus a, a power series centered at a power series about a. I like the centered at a because it gives you a really geometric interpretation of like, hey, we're trying to approximate some function at x equals a and hopefully to the left and right. But if the series diverges, it might not be to the left and right. It might only be good at x equals a. And that's a pretty like trivial, power series if it only approximates a function at one value. Like that's not really all that good. Okay. Actually, do I want to do this one? No, I want to do a different one. All right, I'll do this one. That's fine. Okay, so we want to know when is this power series, I want you to think about this, when we plug in 0, we're going to get 0 factorial times x to the 0. We do define 0 factorial to be 1. Times x to the 0, which is 1, so we get 1. Then we plug in 1 and we get x. Then we plug in 2 and we get 2x squared. We plug in 3 and we get 6x cubed. Okay? And that's a power series. It's a coefficient and a power of x. Okay? So, when does it converge? The ratio test is awesome. All right, so we're going to do the ratio test. You ready? Question, comment, concern?
Can't you kind of already? It doesn't have to be when the absolute value of x is greater or less. Sorry, absolute value of x is less than 1.
I don't know. Is it geometric?
No, but I have a pretty good inclination already that when
All right.
like when you work with factorials, you're going to cancel out to get n plus 1, and so you're going to somehow
So
get
let's
power
see.
of x.
All right, so we're interested in what happens when n gets really big. N plus 1, x to the n plus 1, over n factorial x to the n. Did I do that already? Is that the ratio test? Okay. So, what do we get on the n factorials? Gives us n plus 1
Times x.
times x. Now, as n approaches infinity, what happens to n plus 1? It just gets huge. So this thing, right, the ratio test says, hey, this will converge so long as, right, we're less than 1. Is this thing ever less than 1? No. In the long run, this approaches something huge. This is not less than 1. As a matter of fact, this power series isn't convergent. And it's only a good approximation at its center. Where is this power series centered?
1.
0?
No.
If I had to put it in this form,
0.
0. This power series is centered at 0, meaning that if you want to use this power series to approximate some function, it is only good at approximating that function at one single stinking point. It's
Well,
not very good.
If it's always centered at A, then isn't it always only centered at one point?
So it's always centered at that one point, and it will always be a good approximation for at least one single stinking point, right? But it's really not helpful to us unless it's good at approximating on an interval, or better yet, all x values.
But if A is just a number, how could it be centered on an interval?
So not centered on an interval, but a good approximation, right? So going back to this one, this was centered at 0. Notice this power series did a great job at approximating not just at the center, but also to the left and to the right.
Yeah.
This
No, I
guy,
understand that.
oh sorry,
I'm just asking, like,
I'm just
if you-
answering questions that I know how to answer.
no. Like, if it's always in the form x minus a, like if you can always put in that form, and we're saying that it's centered on a, then it's always going to be centered on a number. And so how can we tell from that whether or not it's also centered on an interval?
So let's do a problem that has an interval. Well, let me go back. So let's take, what is it, x to the n? Was that the one we just looked at? And no, yeah, 1 times x to the n. No, look, the power series one, right? As n goes
We're
from
just
0.
like hoping that it's also on an interval
Yeah,
in
so
addition to a.
right.
Okay.
So if we actually used the ratio test here, I would say, hey, when is this convergent? Well, it's convergent when this is less than 1. Well, what's x to the n plus 1 over x to the n? X. So it's convergent when x to the n is less than 1. What's the nth root of 1? 1. So it's convergent when x, and I guess I should actually, the ratio test would say this. This is convergent when the absolute value of x is less than 1. So this goes back to the geometric series. So another way of proving that the geometric series is convergent when x is less than 1 is by using the ratio test. Now here's the real problem. The ratio test doesn't tell you anything about what happens when x actually equals 1 or negative 1. We know with the geometric series, if x is equal to 1, it's just going to be 1 plus 1 plus 1 plus 1. That's going to diverge. We also know if x is negative 1, it's going to be negative 1 plus 1, negative 1 plus 1, negative 1 plus 1, and that's going to diverge too. So the ratio test is really bad at telling you endpoint behavior, but it's great at telling you if you have an interval. Did that do better or worse?
Yeah.
Oh, all right.
So in this
Go ahead.
example, if then what happens? Like, what would you say?
So now we would say, hey, I know at the very least that this power series converges for negative 1 to 1. That is an interval, not a coordinate. And you want to here's some vocabulary. I would say centered at x equals 0 with a radius of convergence. You're sounding smart. Of 1. So centered at 0, a radius meaning to each side of your center. So a radius of convergence of 1, 1 more than 0, 1 less than 0. And you can also say with an interval of convergence of negative 1 and 1. And then really what the question, sorry, I gotta pause there for a sec. Any questions about new vocabulary? And then the follow-up question becomes, what happens at the endpoint negative 1 and 1? In this case, we know that it does not include negative 1, it does not include 1. But the ratio test would have you wonder what happens at the endpoints. And so your next question is, hey, can you give us one where something more interesting happens at the endpoints, right?
Like a discontinuity or something.
Not a discontinuity, but what if it doesn't? What if it does? What if you had a power series that did converge at one of the endpoints, right? It'd be nice to know. So let me see if I can find one. Don't go anywhere.
We weren't really planning on it.
Great. Okay. Got one. Okay. So I'm going to take a look at this power series. Okay. So do me a favor. Spend the next 2 minutes. Use the ratio test to tell me for what values of x does this series converge. And then we'll talk a little about endpoints. And this is why the ratio test is such a great test. All right. In the long run, what happens to n over n plus 1 as n gets huge? goes to 1. So this question now becomes, hey, if this piece goes to 1, what has to be true about x minus 3?
It has to be less than 3. Or x has to be less than 3.
I'm not there yet. What has to be true about x minus 3? It has to be less than 1. In order for the ratio test to show that a series is converging, the whole thing has to be less than 1. So if I know that this piece is going to 1, that means that, and I really should backtrack. I'm sorry, I've been lazy. I really need my absolute value signs. Okay, so it really means that the absolute value of x minus 3 has to be less than 1. So this absolute value gives us the fact that the series is centered at 3. That's this minus 3. It's centered at 3, okay? And, sorry, I'm wrong. Am I wrong?
I don't think that's right.
That's right, because all I know is a color.
Okay, yeah, fine.
The radius is 4.
Right, okay, so now I have to, what do I have to do? I have to add 3, and then,
And then you then subtract 3 from -1.
so this means either x minus 3 is less than 1, so x is less than 4, or x minus 3 is greater than -1, so I have to add 3, x is greater than 2. So centered at 3 with a radius of 1. I should pause there. Is my algebra 2 okay? Did I do my absolute value correctly? Yes, no? Michelle, question?
Yeah. For power series, are we just always using tricks that are like just applying them in this way, or like
Tell me what you mean by tricks. Like
you
the
like using the a over 1 plus 1 minus r, or using just the
Yep.
There's no new technique for power
Nope.
series. It's just being able to apply old techniques.
Right. All we're trying to do is tell whether or not a power series converges, and if we know, and here's it, we have our strategies for determining whether it converges. Nothing new for that. And then the follow-up question is, after we determine whether it does or doesn't converge, if it does converge, the follow-up question is, to what? Right? We're not totally equipped to answer that yet, but we're getting there. So am I okay with this? So here's what I know. I know that this converges on the interval of 2 to 4, and what I have to do now is I have to check what happens at 2 and at 4. When I plug 2 into this function for x, what do I get? -1 to the n over n. So when I plug 2 in, I get, so let x equal 2, and I get -1 to the n over n. Well, that's the same as -1 to the n times 1 over n. Does that converge or diverge?
That converges.
That converges.
That is alternating harmonic. That converges. So I know when x equals 2, the series converges. Now I have to check what happens when x is equal to 4. What happens when I plug 4 in? Try again. 1 to the n
That diverges.
over
That's
n.
just a harmonic.
And that's just the harmonic. So I know when x is equal to 4, so if I let x equal to 4, I get 1 over n. I know 1 over n diverges. So here's an example of a power series that converges on one endpoint, Gesundheit, diverges on the other endpoint, and on the interval from 2 to 4, it converges. Okay, but you always have to check your endpoints.
Do we know what it converges
No.
to?
Don't know what it converges to. Is that what you just said? Yeah, I don't know this one.
That's like
It'd be nice to know.
So that's how you write the interval convergence. then?
Yep.
Okay.
So that's interval notation from pre-calc maybe.
Wait.
Right.
You can, and you don't have to write it that way. Like if you want to, you can write it as like 2 less than or equal to x less than or equal to 4. Like as long as it's mathematically sound, I don't care about your notation as long as you're okay with any notation that I want to use. Where I'm not trying to trick you with anything new, but I'm trying to, If I use notation you've seen before, I can expect you to do it. Is that okay? Should we do one more? Let's do one more, I think. Hold on. Let me just check. Alright, so we did that. Yeah. Fine. We talked about that. Great. Okay, yeah, I'll give you one more. Only because you asked for it. Okay, that's an N. Okay, go ahead. Give you a couple minutes. What's the ratio test tell you?
X over n. It tells you that it converges for all real x.
No, for absolute
Did you get
x
0?
is less than 1, yeah.
Get 0.
Did you get 0? Is 0 less than 1?
Yeah.
Always?
Yeah.
Yeah. So if you get that the limit is 0, 0 is always less than
So
1,
it converges
that
for
means
all real numbers.
it converges for any value of x you pick.
Sorry, I didn't follow that logic. Could you?
What'd you get for the limit?
It's 0. X over n plus 1 less than 1. I didn't
So it's
know.
1 over n plus 1 times x.
What happens? The question is this. What happens when n gets really big to this value?
The denominator gets huge.
Okay, and so this value goes to 0.
Oh yeah, sure.
So the question is this. I don't care what x value you pick, as n gets huge, n plus 1 is going to dominate. So when is 0 less than 1? Always. And the question is, wow, that's a pretty cool function. That power series converges to something for all values of x. Wouldn't it be awesome to know what function that is? Well, I know what function it is. That function is e to the x. And if I graph it, here's e to the x, and here's the polynomial approximation. Here's the power series approximation. Not bad, right?
It's close for a while.
Close for a while. As a matter of fact, here, if I add more and more terms, it's just going to get closer and closer and closer for more and more. It's not going to be like the geometric series 1 over 1 minus. Yeah, you did this exercise about 2 weeks ago, right? And so that is huge. Like, that's a really, really big deal. That this is equal to the e to the x, is equal to e to the x. Because what that means is this. It means like e to the x is approximately equal to 1 plus x squared over 2. And if I want to know a value for e to the x, I can walk into any like 6th or 7th grade classroom and have students plug in like 0.1 and tell me what e to the 0.1 is. 1 plus 0.1 plus 0.1 squared over 2. Right? I can have them do that a lot easier than explaining to them what e is and how to raise e to 0.1 power. Right? So, depending on what you do later on in life, chemistry, physics, engineering, you might be looking at exponential functions, but you might never use e to the x. You might use this thing. you might use that because it's a whole lot simpler than e to the x. Now, right, you have a calculator or something and all you're doing are basic computations, yeah, you're going to use e to the x. But if you're like using some supercomputer and you're doing like millions of calculations every like second or something, your supercomputer is going to do this so much faster than it's going to do this, which could be the difference between like waiting like days for results or waiting weeks for results, right? And if you only care about some sort of accuracy, right? If you don't care how precise you are after a certain point, why would you wait weeks if you could do it in days? Right. You did a whole lot today. You did a lot. Very impressive. All right, you did so much. I'm not checking homework today. I am checking though, and I'm checking both graded exercises tomorrow.
What do you mean, like the 2 ones from the last 2 days?
Yeah, like last night, the night before. Thinks my fingers have marked up.